All right. Does anybody want to be our class leader for our first online week of class?
I do.
That would be Colin. Right now, I don't have you all as showing. Okay, Colin, I am good for that. So, Colin, if you
Give me 10 seconds. Let me go to my desk.
Where did he have to go to?
I had to go to my desk.
Your desk. All right, I'm looking for your screen, Colin.
Right.
I was going to highlight you.
Uniform.
There you are, Colin. All right, Colin. Can you lead us in prayer this morning?
All right. Class attention. You don't have to stand up. And then, wait, is that 2 Hail Marys?
Whatever you would like this time. So we can do one prayer just for the sake of time.
Dear God, let us have a good day in this online class. Let us learn great things and no goofing. Now let's do a Hail Mary. Hail Mary. Full of grace. Full of peace. Blessed art thou amongst women, blessed is the
Jesus.
Holy Mary, Mother of God, pray for us
Pray for us sinners, now and at the hour of death. Amen.
sinners.
Very good. Thank you, Colin. Okay. So,
What's that, Eric?
all right. So at this time, any last minute questions? Because I'm going to mute you all. And you are able to unmute yourself, as I had mentioned. So if you have any questions, you can certainly shout out, use the chat room, wave me down. All right. So going back to last week, you guys, we concentrated mostly on Newton's second law. So if I call you out to ask a question, I want you to unmute yourself and answer the question for everybody. So Colin, since you are our leader, I'll call you out first. What is Newton's second law that we concentrated on last week?
Force equals mass times acceleration.
Very good. Net force equals mass times acceleration. Excellent. So don't forget this was a vector quantity. Acceleration also vector quantity. So what we saw last week is we had to draw our free body diagrams, right? Often we have weight, a normal force, maybe a force applied, a force of friction. If the force is canceled out, there was no net force in that direction, and your net force determined the direction of acceleration. So I think since Blackboard has been down, I have not been able to grade everybody's work, but it looked like the little work that I saw that came in, everybody seemed to be doing okay. So please send me, if anybody has any questions, thumbs up if we are good on Newton's second law. Okay, we're going to come back to this all the time. When we started this, I said this is one of the most important equations. Newton's first law is law of inertia, which is what we saw. You need a force, you need an outside, unbalanced force to cause an object to change its state of motion. Then we went to the second law, which was actually an equation to put that together. Okay, Luke, do you remember the first or the third law?
Isn't the law of action and reaction?
Very good. So it's often called action, reaction, right? So third law is action and reaction. And yes, anything that I'm writing here on the whiteboard would be recommended that you are sitting and taking notes on this. And again, please flag me down if you think I'm going too fast. But we have this. So often I begin our notes with repeating what we've had in the past. But we did write down action and reaction. I'm just going to repeat it today because we're going to concentrate a little bit on the third law today, which is actually chapter 5 in your textbook. But you'll see by the end of the class, we're going to add a little bit to this third law. So very good. Often called action and reaction. And what this is saying, for every force, there is an equal in magnitude Okay, and this is important, equal in magnitude. Remember, force is a vector quantity, so it has magnitude and direction. So they are equal in magnitude, which is how strong they are, but the reaction force is opposite in direction. Okay, so we want to concentrate on this today, and what exactly does that mean? So I'll pause a little bit for you to write that down. For every force, there's an equal in magnitude but opposite in direction reaction force. So if I go back over here and I think of this, what that's saying is if I have a force in this direction of 10 newtons that acts on something, there is another force in this opposite direction that is equal magnitude, opposite in direction. So Jagan, in terms of net force, if two forces are the same amount but acting in opposite direction, what usually happens with those?
The net force is 0.
The net force is 0. That's exactly right. And if the net force is 0, then there would be no acceleration. Well, then why do we need this? If that would be the case. Okay, so if they were to cancel one another out and not cause acceleration, why do we even worry about it? And the answer is they do not cancel one another out. Because when we talk about the third law, okay, on this one, the forces are on different objects. Okay, the two different objects are what is causing the action, and the second object is what causes the reaction. So in order to have an action and reaction, you have to have two separate objects. Okay, the forces are on two different objects. Whereas over here, when we talk about the net force, we're talking about the force on one particular object. So when we are looking at this, we are talking about forces on one object. Okay, what forces act on that one object? So over here, forces are on different objects, whereas over here, when we talk about the net force, which in this case, these would cancel out and be 0, that's because they're acting on the same object. Whereas over here, you have two different objects interacting with one another, causing an action and a reaction. So they do not cancel one another out, but instead cause motion on one object. Okay? Does anybody have any questions? All right, what I would like to do now is I'm going to do a square sharing of my screen with you. And we're going to take a look and see if we can identify some action and reaction pairs. Okay, so here's some examples of things that you might see in your environment. And the action is something doing something to something else. And the reaction is what does that object do back to the other object. So for example, on this one, we have the fist hitting the wall. So the wall hits back, right? All right, so if we look at number 2 here, or A, let me just take a look at that. So Eric, if I say the head bumps the ball, what would be the reaction to that?
The ball goes flying, or it moves.
Well, that would be the result of it. So if we want to talk about what is the reaction force, so if the action force is the head bumps the ball, the reaction force is the other object, the ball, must do something. What does the ball do? For the head. What does the ball do on the head?
It hits it.
Correct. So the action force would be the head bumping the ball. The reaction would be the ball bumping the head. So what we're saying here, these two forces are equal, But the one object is the head, and therefore it only has this force acting on it. The other object is the ball, and it has this force acting on it. But those two forces don't cancel out because they are not acting on the same object. Okay, whoops, didn't mean that. All right. Let's see, I'll try my eraser now. There we go. Okay, so getting back to this. Oh, you're very nice. There we go. Okay. All right, so let's take a look at the next one. Jacob choked. When I'm driving down the road and my windshield hits a bug, that's the action force. The reaction would be?
The bug doesn't move.
Um,
The bug doesn't have any effect on the car.
it actually does, and that's what we're
Well,
gonna,
like it's a very, very, very tiny.
correct. But
Like,
there is
yeah.
still a force that the bug acts on the car with the same amount of force, but opposite in direction. So I'm glad that you said that. So this is the challenge of action and reaction. They are two equal forces, but we wouldn't say that the bug did anything to the car, but it actually did. And we're going to see that when we're all done with it. It does make a difference with the car, but the car has so much more mass compared to the bug that we don't really notice that there was any force on the car due to the bug. But Newton's third law would say those two forces still exist. All right, let's see. Terrence, baseball players. The bat hits the ball is the action. What's the reaction? Terrence, are you still with us?
Can you hear me?
I did not hear you at first, so you might not have unmuted. So if the action is the bat hits the ball, the reaction is?
The bat has like a low reaction from the ball.
Okay, it might, but that's not, so all of you guys are kind of answering the question as to like how an object would move. All I want to know is what forces would be there. So if the bat hits the ball, that's the action. The reaction is the ball
It's the bat.
hits the bat. That's it. So what we're going to do now after we identify the reaction and action forces is go back and ask ourselves, what does that mean in terms of how does this object move? So right now we're just identifying those forces that would be present. All right, Ben, if my hand touches the nose
touches the hand. Like it pushes
The
back.
hand?
The same force.
say that again.
The nose pushes back with the same force.
Correct. Equal and opposite in direction. So notice all my action and reaction pairs are parallel. The two forces are parallel, but just in opposite directions. If I pull a flower out of the ground, right, the flower pulls back on my hand as I'm pulling on it. You guys all know that. You can feel that, right? When I go to lift weights, right? In lifting the weights, I have to push up on the weights would be the action force. Micah, what would be the reaction force?
It would be the man holding it up.
Well, that's the action. I have to push up on the weight.
Oh, so the weight would be like the opposite reaction.
Correct. So I would say the weight is doing what to me?
Pushing down.
Pushing down. So the action is I'm pushing up on the weights. The reaction is the weights are pushing on me. So I will move according to how that reaction is. I would feel that. So that's how I get stronger, because I have to react to that. Okay, if I think of compressed air, if I'm blowing out on a balloon, on the air out here, the air on the outside pushes back on the balloon. So action and reaction is they are equal and opposite from one another. All right, so let me clear that out there. And scroll down here for a minute. Too far. All right, so let's look at the very bottom. This kind of explains what we see sometimes with ropes and intention. So if I take a look at this one, okay, if I, or the strong man, Tarzan, pulls on the rope is going to pull back on him, right? So that would be an action and reaction pair. You can only have an action and reaction pair where you have two different objects. So the monkey's hand and the rope would be another place of action and reaction. The monkey's hand and the rope, action and reaction. The spring scale and the rope, action and reaction. Here, action and reaction, and you'd have the same thing here. The rope pulls on the tree, but the tree pulls back on the rope. All the way through here, all of those forces would be equal because they're the result of the action and reaction just kind of going down the chain. Those would be your 6 pairs of action and reaction forces. Okay. All right, well, hopefully that makes sense. I'm going to come back to this second page later, but let's put this down in writing so you can put some more of this into your notes. This. Okay. All right, so does anybody have any questions? Raise your hand, give me a signal. Do I get a thumbs up? Makes sense on action and reaction pairs? Everybody good to go?
Yes,
All right,
ma'am.
so then the question, let's go back to Jacob, your comment that, well, the bug's not going to do anything to the car, right? Because the bug hits the car, but yet there is a force on the car. So what effect is that force on the car going to have?
It's
So let's
not really.
right.
It's not really gonna have any much of an effect on it
Okay.
because the car's mass is a lot bigger than the bug, and not only that, it's coming at a greater velocity than the bug is. So
it's a combination of both. I'm glad you said that, which is what
Good
our
choice.
topic is today. The combination of mass and velocity. How do I put those two together? So let's go back to this, everything that we had in our notes before. And I only have so much space here. I do miss my big classroom whiteboard, but I'm going to have to erase this. But I want to keep these two concepts up here. So if we think of the car and the bug, right? Two different objects having a very big mass. Let's say that mass is 100 kilograms. And then we look at the bug, even though it's much, much smaller than this, and it has a mass of 25 kilograms. So this is just a scenario of two objects, any two objects coming together that have two different masses, one much bigger than the other. Let's say I bring those two objects together, similar to me, you know, I love my volleyball. So, similar to me hitting this volleyball, right? I have a certain mass, I'm gonna come in and I'm gonna hit the volleyball, right? So, Jacob Rose, if I hit the ball, what does the ball do to me?
It doesn't have the equal force, so I guess it flies off your. It hits off, it bounces off your hand.
Okay, so if I hit the ball, that's the action force. That's correct. The ball is going to hit my hand and push back on me. So that's kind of the scenario that we're looking at here. I have a much bigger mass than what the ball does. I definitely have more than 4 times the amount of mass, but that's kind of the scenario. So if I push on the ball is going to push back on me, right? But I should drop more like this. I push on the ball and the ball pushes back on this object. So on this object, it would have weight, a normal force, and then this force from the ball pushing on me. Over here, you would have smaller weight, smaller normal force, right? And then it would have a force going in this direction. These two forces are equal to each other. This normal force and that weight are equal. They're going to go out. This normal force and that weight are equal. So the only net force acting on each object are two forces that are actually equal to each other, right? So let's see. Okay. Sorry, just playing with my computer there. But let's now then put these into this equation. let's say that these two forces that act on each other, so the force on object X and the force on object Y, are equal because they are action and reaction pairs. So I'm not going to put the vector symbol up there because they're only equal in magnitude. They are not equal in direction. They're in opposite directions. So in this case, they are action reaction pairs. Okay. So if I apply Newton's second law to each one of these free body diagrams, right? In this case, we'd have negative 100 newtons acting to the left, causing an acceleration on object X. So we just look at object X and object Y in terms of Newton's second law. Then when we take a look at these, the force on it, mass X, acceleration, its force was negative 100. Let's write it like this. Force then divided by mass equals acceleration. And I can still say net force, right? So this would be 100 newtons divided by 100 kilograms would be the acceleration of object X. Okay? So Jackson, easy one, was 100 divided by 100.
Sorry, 1.
1, and its acceleration, so what would be the units?
Meters per second squared.
Very good. So this is 1 meter per second squared equals my acceleration of object X, which was the big one, right? I do the same thing on object Y, and I guess I should have written that as a negative, and it's going to be in the negative direction because it does have a negative value. But its magnitude would be 1 meter per second squared. If I take a look at object Y, when I take a look at object Y, it has a smaller mass of 25, but the same force is acting on it because it's due to the reaction of the two colliding together. So for object Y, we still have the same equation that the net force on it equals mass times acceleration. Its net force then divided by its mass equals acceleration. So the net force on this one is a positive 100 divided by a mass of 25 kilograms equals that object's acceleration. Wilson, I think you joined us. Do you know what 100 divided by 25 is off the top of your head? You might have to unmute yourself.
4?
4. Is that you, Wilson?
Yeah.
All right. 4. Very good. 100 divided by 25 would be 4. And what are the units again of acceleration, Wilson?
Kilogram?
That would be mass. So acceleration is?
Acceleration is
Look over here.
meters. God, I don't know what it's called.
Meters per.
Meters per second squared.
Very good. All right, so this would be 4 meters per second squared equals acceleration. Excellent. All right, so Jacob choked. Back to what we had said with the bug and the car, right? We haven't changed anything we said about Newton's second law. These two have the same force acting on them, but because they have different masses, they're going to have completely different accelerations. And actually, one acceleration is going to be in the opposite direction as the other one because the forces on them are in the opposite direction. Now, that's ignoring all other forces. The car could have more friction on it, right, compared to the bug and so on. So you would still consider all the other outside forces that might be present on either object. But if you are just looking at how do these action and reaction pairs cause motion between two things, how does my body cause this ball to go so fast when I hardly move, but there would be a little bit of a pushback when I go to hit that, right? So I can make that go really, really fast because it's very light. So with the same force on it, it can have a high acceleration compared to my low acceleration, okay? But with the understanding that I put a boundary about this, so my force on it is an outside force on the object causing a net force, okay? The two forces together are two different objects. Those two forces are action and reaction pairs if we're talking about two different objects. Okay. All right, back to here. Thumbs up, we all good? Any questions? All right, staying with me? All right, so let's go back to, we'll do a screen share here. And let's see if we can answer these questions. There's one really tough question on here. We'll see who I'm going to call on to get this one. All right, so Nellie Newton holds an apple weighing 1 Newton at rest in the palm of her hand. The force vectors shown are the forces that act on the apple. So if we go back to our original thing, right? We have weight pulling down. It's sitting on her hand, so we would say there's a normal force pushing up. Okay, to say that the weight of the apple is 1 Newton is to say that the downward gravitational force of 1 Newton is exerted on the apple by what? So Terrence, what's causing the weight of 1 Newton? The earth or her hand?
What's the question?
If you look on your screen, A, to say the weight of the apple is 1 Newton, the gravitational force of 1 Newton is exerted on the apple by what?
Oh, the earth.
By the earth. So we all know we have weight because of earth, right? Nellie holds the hand to support the apple with a normal force N, which acts in the direction opposite to W. We can say N equals W, right? And the reason we say that is because there's no acceleration. So these two forces are equal. Since the apple is at rest, the net force on the apple is, Micah? Since the apple is at rest, the net force is?
0.
0. Very good. Because acceleration is 0, right? So these two questions go hand in hand. You got to answer one before the other and vice versa. All right, here's the hard question. Everybody pay attention, and then I'm going to call on somebody. D. Since N is equal and opposite to W, we can or cannot say that N and W comprise an action-reaction pair. So they are equal to each other. That's what we set up here. But opposite in direction. And I apologize, Terrence, you answered this first one. I did this one way too quick. This answer should be that they have the same magnitude. They are not equal to each other because they have different directions, but they have the same magnitude. All right, so if we go back to D, since they are of the same magnitude but opposite direction, are they action and reaction pairs? Jackson, what do you say to that?
Wait, for the can or cannot, or for the?
For part D, can or cannot?
Okay. I would say that, I don't know.
Are they action and reaction pairs?
At first I was thinking can, but since there's no direction, wouldn't it be cannot?
Well, at first, remember what has to be true. So they are equal, right? We said that they are equal and they are opposite in direction, but they act on what?
The apple.
Just the apple, right? So they're acting on just the apple. So because they are acting on just the apple, then that means they are acting on one object. So that means they cannot be action and reaction pairs, because action and reaction always act on different objects. And here we see the normal and the weight are both acting on the apple. So the action might be the apple pushing down on the hand, and then the reaction, the hand pushing back up on the apple. So if I throw the hand in there, then I would say I have an action and reaction pair. But if I'm just looking at what forces are acting on one object, then those are not action and reaction pairs. They are just forces coming from outside objects. So part E, in accord with the rule, if action is A acting on B, then the reaction is B acting on A. If we say action is earth pulling down on the apple, then the reaction is the apple pulling up on the earth. And if I go back to our calculations that we had, the mass of the earth is huge, right? So we're not going to go through all that. If we go back to this, and I put the mass of the earth in here, that's huge compared to the apple. So yes, the apple does pull up on the earth, but the earth's mass is so big that we don't notice that at all. Okay, so you got to be very, very careful. Colin, are you entertaining everybody today? Nothing has changed.
I'm just on my phone texting my mom.
Oh, okay. I forgot to say, what I do usually request is that you all shut off your videos so you are not entertaining each other and just watching each other, because that's very distracting, right? Hopefully you have it in kind of speaker view, but yeah, if you want to shut off your videos, but then every now and then I want you to put them on. So keep them on for a moment, and then when I start teaching again, I'm going to shut them off. All right, so when I like them on is when I just ask you, is everybody following along and everybody clear on that?
Just do the thumbs up emoji.
If I'm holding this, right? The action would be the ball pushing on my hand pushing back up. That's action reaction if I look at my two separate objects. But if I just look at the ball, which would be like the apple, right? Then the normal force and the weight are not considered action and reaction pairs. All right, so why do we want to take a look at this? Because when I interact, two objects interacting with one another, all right, so I'm going to go ahead and keep you all muted, so you can go ahead and mute and shut off your video, and we'll go back to, there we go. All right, so why is this important? Let's go back again. Jacob, you said it has to do with the mass of the object and that the car was moving so fast. So if we take a look at both of those two quantities, the quantity of mass and velocity together, we have our next concept, which is momentum, okay? And that comes right in here with all of what we're saying right here. So in order to really better explain Newton's third law, along with the second law, sometimes it's helpful to understand it in the concept of momentum. So this is our new chapter, chapter 6. Get rid of all this. Momentum. Okay, so momentum is a vector quantity that depends on mass and velocity. So it's a characteristic of an object that depends on its mass and its velocity. I can have momentum or I can have no momentum. So it's a description of a quantity that I can have. It is a vector quantity. We're going to deal more with this on Thursday, for your class on Thursday. But for right now, let's go ahead back to Newton's second law. F equals ma. So we keep coming back to that. Again, vector quantities, right? So Jagan, do you remember the definition of acceleration?
The rate and change in velocity.
Excellent. That's perfect. The rate of change of velocity. So acceleration is equal to the change in velocity over change in time, right? So I said it. But remember that this delta means change in, right? So we had it as a final minus initial. So if I want to think in terms of velocity and an object's mass, I might want to look at acceleration not as an A, but rather that it's a velocity per time. So if instead of using the A in our equation, we plug this in for acceleration, then we would have the equation saying that the net force, the word net, is equal to mass times the quantity of change in velocity over change in time, right? So our net force would be change in velocity over change in time. Now, I have velocity in my equation, not just acceleration. I have mass in my equation. So Jacob, just as you mentioned with the car, mass and velocity do make a difference on forces and so on, how an object is going to be moving. So to look at this equation in a little bit of a different way, I'm going to put the t over here, okay? So let's multiply both sides by the delta t. So that gets rid of it on this side. And then just flipping those, x times y is y times x. So we'd have the net force times delta t is equal to mass times delta v. Okay, that's our new equation that we're going to be working with over the next couple of weeks. And what is this equation telling us? Okay, this side of the equation is what we would call change in momentum. That's our change in momentum. Momentum is a mass times velocity. So if I want to change an object's momentum and change its velocity, then I'm going to have to apply a force, right? So we already knew that. We're going to have to apply a force. But when I apply that force, it matters how long I apply the force. So this equation allows us to consider that when I hit this ball, doesn't matter whether I hit it like that or whether I hit it and follow through. So when I go to hit the ball, pull it down there a little bit, I can do a little tap on the ball, or I can have my hand be in contact with the ball for a long time period. So something we haven't talked about yet in how do forces cause changes in motion is what happens if I apply those forces over a long period of time? What effect does that have on the motion of an object? So playing baseball, right? Terrence, when you hit the ball, you can either tap it, right? Give it a little bunt, or you can follow through and swing for a long time. When I kick a ball, golf, right? That follow through means I'm applying my force over a long time period. Whereas if I just tap it, I'm the same person, so the force that I can apply can only be so much, but the amount of time that I take to apply that force is my other control in the game of how I can change how that ball is going to come off my club head, my foot, my hand, the bat, whatever it is. So as much as I can hit the weight room, make myself stronger, I can also be in contact with the object for a longer time to cause a greater change in velocity. So this equation really comes from Newton's second law, where we defined acceleration to be change in velocity over change in time. We derive it in this way. These two equations are exactly the same thing. It's really Newton's law. But we define this quantity of mass times velocity, we give it its own word, which is called momentum. So the quantity of mass times velocity is an object's momentum. Okay, put your videos back on. Colin, I like it. We match. Are you a volleyball player? Are you muted? All right, everybody can unmute themselves.
I'm really good at volleyball. I'm really good at serving.
All right, so what do you think? Should we get a team going at Benedictine next year?
Yes, I'll play it over soccer easily.
Yeah, I'm tempted. We'll see.
Awesome.
All right.
Roger Weaver, would you be the coach?
Questions on what we covered here today?
Mr. Roger Weaver, make a volleyball team. I'll play.
Only
You'll play
40
too?
sports.
That'd be fun.
It would be fun. It's a great sport. Charlie,
So is mass directly proportional to velocity? Is that right?
no, you wouldn't say that. So mass and velocity are two different quantities, but mass is directly proportional to a change in mass is directly proportional to a change in momentum.
And momentum would be mass and velocity together.
Correct.
Okay.
So we're going to put some numbers to this, and you guys do much better when we actually put values and do calculations with it. So that's what we're going to do on Thursday. So what you'll read in the book is kind of just exactly what I've gone through here, explaining that a little bit more. But the reason you want to do momentum is now we're going to study collisions, right? Two cars coming together and colliding. It's hard to figure out what forces are between there, but it's easier to figure out how much velocity did I have coming in, how much velocity do I have coming out. So then we can kind of work things backwards and figure out all those forces and things. Okay?
Charles, are you wearing a collared shirt?
Charles, I swear, if you're wearing a collared
Oh
shirt,
my gosh.
No,
And
I'm
make sure
wearing
y'all wearing a
sweater.
collared shirt.
You guys should be.
Terrence, let's see the check. Let's see the check. Come on. What are you wearing? Good job. Good job.
I like were the options Benedictine shirt or collared shirt, right?
I forgot to do the uniform check in the class. What was it called?
You just forgot it was a spirit.
that's what you're calling.
Charles.
Say something.
Okay, gentlemen, real quick, refocus. I have a quick question for you. This is serious because a lot of people's grades changed a good bit from our Boot Camp Friday grades.
We had a boot camp Friday.
Who can juggle? Who watched my video and learned how to juggle?
I did.
You can only do 2 balls.
Show me a little bit right
You're
now.
on it, but it's hard.
Go get the balls. I want to see who's been practicing.
I tried. It's
I got you.
impossible.
You have to
I
keep
tried.
trying.
I could not do it.
Jackson,
Yeah,
it took me 2 months.
Mr. Roswell, I can barely do the thing where you go.
No, Terrence, I don't think that's 3 balls. That's the
I can't
same
find it.
ball.
Thing with this Rosemary, I'm swinging it.
Terrence,
I'm not even kidding. I'm
One
swinging it.
ball.
I
The
juggled.
same thing
I
I
can
did.
juggle.
You tried to the left.
I can
I'm
juggle.
on it. I'm kind of nice at it. I just don't have any balls right now.
I'm killing
Okay.
it.
All right,
got
Jagan, you're on.
Yeah,
Parents, it just looks like it's throwing up the same ball over and over.
Jagan, don't use those baseballs around the picture.
I did it.
Marshall, it looks like you're doing what I did, which is toss my ball to my right hand. You did the same thing. You got to practice tossing it up. Okay, now, gentlemen, here's how this is going to work. You guys are all going to send me a video on Friday, or I'll maybe even give
I
you
have
another
one
weekend
juggling
class,
ball.
but not on Friday. And your class will be ranked on what's your total time that you were able to juggle. So I'll watch your video and I'll time how long you juggled consecutively. And then I'll divide by the number of students in your class, and whichever class had the longest time of juggling is the class that will win. So you guys as a team have to figure out how to juggle.
Guys, you just throw the ball up there and then catch it. You throw it back up.
Okay, Colin, that's pretty
Colin, don't
much
throw
it.
it back.
Throw in
Don't
another
throw it back,
ball.
Colin.
So, Marshall, do you see what you're doing there?
Yes.
You're tossing it to the other hand. That's what I did.
The IQ.
Jagan might carry the team here, it looks like. Jagan's
Do we
pretty good.
get extra credit for winning?
Please say someone heard that.
You do get extra credit if you win by
Did
the end
y'all
of the
see
49
that?
weeks.
All right, our
Oh.
entire class is going really try hard, and we're gonna win this.
You
My
need
dad
to
knows how to
win.
juggle. I'm
Did anyone see just made me flip my computer?
I can do
I
5
was
seconds.
trying to
next year.
juggle. My computer went behind my monitor.
Don't break anything. Jagan, you need to stop. You're going to break something. Wilson, you still with us? Did you even give it a try? Can you try it for me? It's good for your head.
You know what's good, Miss Weisenweaver?
Want me to do?
You know what's good, Miss Weisenweaver?
What?
What want me to do, Miss Rosenberg?
Juggle.
Oh, how many things to juggle?
Pistachios.
Can we leave?
They're pretty good.
Pistachios are very good. All right, gentlemen, that concludes our class for today. I'll see you all on Thursday. Your homework is to read, brush back through all those. How did class go for you today? Is this going to work? Give me a thumbs up.
Honestly, math was really boring.
Math was boring. Well, how was physics, Colin, since we had
Better.
volleyball?
I mean, oh yeah, that was pretty good. I mean,
Can you set?
oh yeah, I'm really good at that too. But I gave it back to my sister. She's
Oh.
horrible at volleyball. She thinks she's good.
Dang.
I might go out this evening and pass it around a little bit, get something to do, something physical.
She's like on a team, but like I'm on like the varsity for Trinity. No, I mean,
Colin, don't you play travel volleyball?
With our Richmond Volleyball Club?
maybe.
All right,
Great, Colin.
boys, unless you have a question, you may log off, and I will see you on Thursday. Anybody who wants to stay behind who has a question, I have about a minute or two, but I do have a next class. So have a great day. Nice to see you.
Bye, Ben.
Bye, Colin.
I'm teacher's
Bye.
pet, so I'm gonna leave last.
I'll see you later, Charles.
Bye,
don't
Dan.
know.
I have a quick question.
Yes, Charlie.
You think you're gonna leave
So,
first, Charles?
It's none.
So for when you had X as 100 kilograms and Y for 25 kilograms, so how did you get? You wrote down f of x equals f of y equals 100 newtons. Could you go over that again? Because I kind of got like.
I just made that up. I made up a number because all I said was they had to be equal to each other.
Oh, you're just making up a force.
Correct.
Okay, and then why would you put net force over mass? Like, why did you do that again? I wasn't.
Because that's our equation to solve for acceleration. I wanted to know, so we were talking about how each object would move differently because they accelerated differently.
Oh, okay, I see. So you're isolating